preferred to xh, and there is at least one subject k such that yk is strongly preferred to xh. This is by definition, simply by definition. Now, let us begin to employ our assumptions. X is equal to the negative ortant. What happens? This yk, which is preferred to another bundle xk, cannot be equal to the null vector, because by strict monotonicity it is clearly impossible that the null vector is preferred to another vector of a non-negative ortant, which have at least one positive component. So, yk is not null, and there is at least one component which is positive. In our case, is the first component. So, here there is xk, the original point. These are the preferred elements. I put yk here. The quantity of good 1 is a positive number, while the quantity of good 2 is equal to 0. This is not necessary, of course. I consider only the extreme case. Now let us employ continuity of preferences. Since yk is preferred to xk, it is possible to reduce slightly the quantity of one good, for example, our case good 1, and to go in the bundle zk, and zk will be preferred to xk by continuity. What are the components of zk? The first component is yk1 minus a certain positive epsilon, which is simply the length of this small segment. All the other components are equal. In other terms, you obtain a bundle which is preferred to xk by saving some quantity of good 1 with respect to the bundle yk. What is the use of this epsilon, this quantity epsilon? It is redistributed, for example, in equal parts among all the other subjects. Consider another subject, h, different from k. Give him this quantity of good 1, epsilon on h minus 1, while all the other quantities containing the vector y are equal. So you obtain a vector zh, which has one component greater than yh and all the other equal. By strict monotonicity, zh must be preferred to yh opposite. Moreover, since you are reducing the quantity of good 1 for the subject k by epsilon, and you are adding to every other subject this quantity of the same good 1, the total variation in good 1 is 0. Clear? So, substantially, the sum of these vectors zh is equal to the sum of yh. In this sum, clearly, there is also k. So to speak, the allocation, the vector z1, zh is a reallocation of the resources of y. So it is another possible allocation. Let us compare this allocation z with the original allocation x. For the k subject, there is preference. Zk is preferred to xk. For all the others, well, we know by strict monotonicity that zh is strictly preferred to yh. But we know by assumption that yh is weakly preferred to xh. And since the weak preference relation is transitive, by a well-known theorem consumption theory, we obtain that zh is strictly preferred to xh. If z is strictly preferred to y, and y is weakly preferred to x, z is strictly preferred to x. Pacini surely proved this result in consumption theory. But in sum, what happens? That every subject with the bundle given in by the allocation Z is better than with the allocation X. But this is impossible, because X was a weak Pareto optimum. In other terms, it is not possible to ameliorate the condition of all subjects by means of a redistribution of resources. Is it clear? Contradiction. And therefore, pi W is a subset of pi S. And in the end, you can write this equation. Is it clear? Oh, sorry, this is a difficult theorem. Was proved, a proven alternative proved is, for example, Mascolel, but is due originally to other debris. Well, let us have another break.